RISC-V, AI, matrix, PPA. We roll all these terms off. We're building amazing things. Minor problem, we've got to get them right? Verification remains a big problem. You're going to build big complex systems. We've got to test them. You can write these tests, or you can use tests that other people have built and have been used on many designs. Brecker is a verification company. We're in the business of test synthesis, and all this really means is that from a single source of truth, we synthesize test cases for multiple test benches. So a key point to you over here is instead of having to modify your test bench to work with our tests get modified to work with your environments. And one beauty of this is that the tests can be synthesized for simulation, for emulation, for FPGA, for post-silicon, and this means you always have test content ready to go, whatever stage of design you're ready on. My presentation is organized largely as a tutorial. We all know we're going to build systems. We all know we're going to build systems around RISC-V, else you're in the wrong conference, right? And we know there are many things to deal with, but the specs are complex. There are many things to take care of. And this is largely a tutorial of some of the things that we need to worry about in SoC verification. That's what I'll talk about in the motivation. Then I'll spend a little bit of time talking about how each of these pieces work, again, mostly as educational on, what is going on some of these pieces. What is MMU? What is AIA? What is IOMMU? Then we'll talk a little bit about system VIPs. System VIP, you're used to the idea of buying a protocol VIP like for PCI Express, right? You'd never write tests for PCI Express yourself anymore. You just buy something from one of the major vendors. Well, you can buy those solutions for system VIPs as well, for RISC-V subsystems, and so on. And then if we have time, we'll get a little bit into what we're doing for debug and coverage. Okay, RISC-V subsystems, right? When you build an ARM-based system, you're using a core that 1,000 people have used. When you're building a RISC-V-based system, you're using a core that there are 100 different cores and 10 people have used each of those cores, right? Notwithstanding our friends at Andy's over here who have possibly a much larger user base, right? But when you plug them into systems, that means as an integrator, there are many places for you to screw up. This problem is recognized enough in industry and by EDA now that Brecker has been working closely with Siemens EDA and Signature IP to build a reference platform around RISC-V that has all the protocol IPs, the system VIPs, the CPUs, everything in there so that you have a great starting point to work with, right? So this is an important enough problem that multiple companies are working together to start solving them. Okay, so let's run through some of the things we need to worry about in system verification. We talk about things all day long, but have we really thought about how to verify them, right? So one of them is, okay, we have a single CPU, that's cool. We have on-per spec, we have a per spec, we know we got to do all of those, okay. But once you start putting multiple CPUs in, you start thinking about coherency, right? You think about atomics. So you can't test atomic on one core, you need multiple cores. How do you test that atomics are correct and that you're really getting a lock on a piece of memory? How do you check that your memory ordering is correct? If it's not, your system will fail to work correctly with software. You've got caches all over the system with a high-performance design. How do you know the caches are working? There are multiple levels of caches. They all have different protocols. How do you make sure they work? Interrupts. Every system must have interrupts of some kind. We have a wonderful specification for AIA, the Advanced Interrupt Architecture. It's a beautiful thing, but the spec is hard to understand, right? There are these interrupt files, the so-called IMSICs, where you can write to those locations to tell that CPU, hey, I need to interrupt you. Those interrupt files live at different levels of privilege. And you have a so-called APLIC, an Advanced Platform Level Interrupt Controller, I think it stands for, right? Interrupts can come in from outside the subsystem, basically your DMAs and your uncore IPs. Those can be reported to the system either through wired interrupts or through messaged interrupts. Okay, then we've got to worry about memory protection. Okay, so there's such a thing as a MMU. This is the virtualized memory on the CPU. This is, most people know what that's doing. There's PMP on the CPUs, physical memory protection of certain areas of memory. But life gets more complicated when you have to bring in the IOMMU. So this is allowing, say, an operation on an uncore DMA to come through virtual memory without having to ask the CPU for every translation. There's the IOPMP, which is physical memory protection for the IO devices. Again, security. We saw this in some of the Andy's slides. Almost everything that's high performance will have some kind of PCIe in it. The PCIe has to interact with the IOMMU, so there's a lot of complexity to what needs to be verified. Then there's debug and trace, right? This thing has to work, because we're almost certain we would have trouble with either something in the chip or something in software. Well, it isn't that simple, right? This is a JTAG-based systems. So what do we do about all these things? So there are lots to worry about in this system. I'm only talking about 3 different topics over here. So let's get a little bit into understanding the intent of the RISC-V specification, right? This is coming from, we are talking to enough people working on enough designs that we realize that not everybody understands what the basic idea behind a lot of these mechanics is. So just talking through what they do. So let's talk about our atomics, ordering, and cache coherency. So cache coherency, most of us have some idea of what we're talking about, right? We have caches that have a copy of the data. We've got to make sure when somebody wants the data, they get the right copy. So you can have a coherent write coming from one core, that's fine. But that might need to be combined with a write to the second half of the same cache line coming from another core, or all 4 cores. That in turn might need to interact with IO coherent accesses coming from PCIe. So that means PCIe is trying to read some address, it has to snoop it out of the cache. Those reads might be coming from DMA. So all those different kinds of operations, they need to resolve out, and the right data has to be served to each of these elements. Cache coherency verification is an art unto itself, right? It's an area that Brucker has done a lot of work in. There are many strategies for doing it. One interesting strategy is to say, go pick a set of interesting addresses, put crosscuts into them so that the greens make one set, the yellow makes one set, the blue makes one set, and then have different agents work on different pieces of that memory. And the idea is you're creating massive contention for cache lines, some coming from DMAs, some coming from PCIe, some coming from CPUs, and see if the system holds together, right? As the systems get higher performance, they are harder and harder to get these things right. It's easier and easier to find bugs. And the idea over here is you run these loops free running. If you are running in emulation or post-silicon, you can run them 5 minutes, half an hour at a time. Because when you do this kind of stuff, you do find edge cases that were missed in simulation. Okay. And the punchline over here, of course, is when you look at all this coherency verification, you will see massive coherent traffic going across your NOC as everybody's arguing for the same cache lines. So this is caches. Let's talk about the advanced interrupt architecture, right? So there are multiple pieces to the AIA. The first is this so-called IMSIC, right? Don't ask me to, incoming message signaled interrupt controller, IMSIC, okay? And the idea is, here's a set of addresses that if anybody writes to that address, it is indicating to that CPU that, hey, I'm trying to give you an interrupt with this minor ID, right? Okay. Well, those can be written by other CPUs. This is a CPU to CPU interrupt. It can be written from PCIe. PCIe already had this idea of message signal interrupts. Interrupts can come from some uncore IP like a DMA that'll go to the APLIC. Interrupts can come in from outside the subsystem. Those in turn can be delivered to the CPU either by doing a message signal interrupt, which means we're basically doing a memory write to this IMSIC, and that's how we tell it. Or there can be a special wired interrupt. And in a second, I'll talk to you about the pros and cons of each of those. So carrying on with the IMSIC, there's one IMSIC per heart. There are usually multiple ones for each level of privilege. It's an interrupt file at a well-known address with well-known offsets. And in the system, we can signal interrupts by simply writing to this interrupt file. Now, this is some pros and some cons, right? On high-performance systems, we're just doing a memory write, and we don't have to wire up separate interrupt lines, so that's the good news. The bad news is we don't know the latency of that write. If there's a lot of other traffic going on in the NOC, it might be slow. Some systems don't care, some systems really care. So real-time systems tend to use wired interrupts. Separate interrupt files for each privilege level, and sources of interrupts, right? You've got to test not only CPU to CPU, on-core IPs triggering those, PCIe message signal interrupts, APLIC-driven interrupts. My point is a lot of different things to verify at the system level. Okay, let's get a little bit into the APLIC, right? These are all things that are mandated by the RISC-V Advanced Interrupt Architecture specification. So it's a block that sits in the subsystem. So it's not part of the core, it's part of the system. And he is deciding that as each interrupt comes into him, who should receive it. So this is programmatically defined. You can forward those interrupts either with a wire or with a message, depending on what you need in your system. It's got its own memory map control region, right? A complicated region to go after. You can delegate the interrupts to lower levels of privilege. Telling you a little bit about what the fields in this memory map structure means. All things that need to be tested. Okay. Let's talk a little bit about memory protection, right? The IOMMU and the IOPMP. So we have memory virtualization, right? So any system we need. Software wants to think about all the memory in the world existing, but some of it may be paged out, paged in. This is all done with virtual memory. We're used to this. And now we talk about hypervisor, where there's two levels of mapping so that you can have a guest OS running on your local machine. The idea behind this IOMMU is that a guest OS might be running some program that is using a DMA in the system, and the IOMMU lets you map to whatever the virtualization for that hypervisor system is. Okay, and each IOMMU might be talking to multiple on-core IPs, where each of those IPs are in fact running a different process, which means there's a whole lookup scheme going on, something called a device directory table and something called a process directory table. I won't get into all of this, other than to make the point that there's some piece of hardware sitting out in the system who at this current point is being used by some application being run by possibly a guest OS. And we got to figure out, okay, who's asking, which process do they belong to, therefore which virtual memory map are they trying to play with, right? Complex stuff. These IOMMUs, they can get things like page faults. They got to tell the CPU, hey, I got a page fault. You need to page in this piece of memory for me. So that in turn gets us into a scheme of command queues where the IOMMU says, hey, CPU, I need you to go worry about this for me. And the CPU eventually realizes, oh, there's something for me to go, fixes it, and lets the IOMMU say, okay, I'm done. You can carry on with your work. Again, a good deal of complexity of different things that need to be verified. Okay, let's talk about debug and trace. So debug is, OCD, a lot of buck, right? How do we connect to JTAG and debug our chip or our system when it's in the lab? So we have a RISC-V debug specification. It does quite a lot, right? So you can trap on various conditions when you execute a particular address or when you write to a specific address and so on. The idea is that JTAG connects to some translation layer to this debug logic. You can put custom code in the debug module that gets run by the debugger. You can run code and trace its execution, so all these things can be done. Okay. So those are the problems, right? And those are the things we've got to go test. So let's talk about some of the solutions. So what Brecker does is test suite synthesis. We sell system VIPs, pre-built solutions to these problems. These are libraries that can be plugged together to build various systems. And the idea is that there's some system VIP that goes into some tool that spits out some C program, usually with inline RISC-V assembly. and it also has a mechanism for coordinating with what's going on the test bench side. And this is how we holistically test the whole system. So we use graph-based models to capture our search space. And without going into a great lot of details, right, this is just the graph for how we build page tables. And you can go through, see different parts of the graph doing different decisions. But the punchline of this slide is even on this one graph that's just a submodule of some system VIP, there are 2.2 times 10 to the 138 possible paths that we can go test, right? So we have a lot of testing that's possible. There's only a small number of these tests that can be run in simulation. We can run a bigger population in emulation, but there's a lot to do. Okay. This is an example of the kinds of tests we will generate, right? So we have some debug view where you can see what the test looks like. In this case, you're seeing one core with, with multiple threads running on it, and we can walk through the various stages of what the test is doing. Here's an example of an AIA test, which maybe is a little bit more interesting, where we are randomizing the AIA configuration, we are setting up trap handlers, we are driving an interrupt, and then we are checking to see that the right interrupt was properly reported by the trap handlers. Okay. And then you do this concurrently, right? So to finish up, let me talk a little bit about debug and coverage, and then that'll be my time. So debug. We found that as we're generating test cases for big complex systems with many cores, figuring out when something is wrong, who went wrong, and why it went wrong was an issue. So we got to this idea of system-level debug. And the idea is the tool will give you a picture of a test case. This is a map of the test case, and it'll tell you exactly which node failed. You can associate that with what memory addresses were used. You can associate that with the error message and exactly where in the code that error came from. So you can very quickly drill down to which core, which operation got unhappy, and then you can debug from there. We are all interested in coverage and coverage closure, all right? But it gets hard to think about coverage once you get past the basic functional coverage of, did I tickle my RTL, right? How do you know that you did all these use cases? And that's what these graph-based models are great for, right? So the tool will automatically measure which paths through the scenario model have been exercised. So this is stimulus coverage, and the idea is you use it in conjunction with your functional coverage. We're not trying to throw out what is there. We're simply saying that you need more coverage cases than you could possibly measure with your functional coverage, and that's what these tools are good for. Okay. And then, of course, we're trying to get 100% traceability from the ISA specs through our test plans to these coverage models so that we can say definitively that every single thing in the plan has been exercised. Okay.